So a major source of model error in weather and climate prediction models is clouds and precipitation. Until recently, observations of clouds and precipitation have been studiously avoided in data assimilation. And I would say there's a connection between that fact and the fact that clouds and precipitation, well, they're sort of interrelated. Clouds and precipitation are a major source of model error. And I think the history of numerical weather prediction is, as we assimilate data relevant to certain variables, we discover the errors in our models of those relevant variables, and then that helps us figure out how to fix them. So I think a lot of people have looked at clouds and precip and thought, oh, it's so small scale. If we do a better job with that, it probably won't add much to the predictability time that we have, where we get useful predictions. But as you know, clouds are really, people really care about clouds. If you think about solar power, you know, they're interested in cloud forecasts at very short timescales. And then the other big one here is we know that clouds and precipitation are probably the major source of climate change prediction uncertainty. So I just think this is a really important problem. And, you know, the three challenges I listed there, I mean, they're not just associated with clouds and precipitation assimilation. A lot of them pertain to things like ice, wind speed, observations, some other things. But if we could really get on top of these, I think it would be helpful. Yeah. So what are we trying to do here? Where would we like to be with our data assimilation experiment? And so to help try and get everyone on the same page with that, let's do a little thought experiment. So imagine an infinite number of replicate Earths. They have the same solar greenhouse gas forcing, but say the butterflies fly in different directions. So chaos has kicked in, and each replicate Earth has an independent realization of today's climate. So you're kind of seeing the instantaneous climate at a certain point on our trajectory of greenhouse gas forcings. And let's assume that the same observation types and locations are present on each of these Earths, but these observations will incur different random errors of representation and instrument errors. Yeah? So let's suppose we go to our Earth and look at our GOES 16. All the other Earths have a GOES 16, and they're looking down at this portion of the Earth. And anyway, on our Earth, when you look down from space, this is what you see, this amazing, evolving cloud field. And you can see that there are large scales there. There's also lots of small scales. You can just spend hours looking at this thing, and all the little details, long time scales, short time scales, big space scales, short space scales, some of them intertwined. Now we've got some convection taking off. Okay, so we've got an infinity of these replicate Earths, yeah? So within that infinity, we could find a sub-infinity that had a movie loop, all the Earths that had a movie loop that looked just like that, yeah? So each of these Earths had a different error of representation for that movie we were seeing there. Each of the Earths had a different instrument error. So the actual truths behind this will be different. There'll be some distribution of true states associated with that movie loop we just saw. And of course, this is just showing a rather small portion of the Earth, so everywhere else there could be big differences. But what I'm going to say is that should be our objective, to get data assimilation schemes that could give us this distribution of possible true states, say, given a movie loop like that. That's sort of a big ask, so that's where we want to go to. And so part of getting to there is having these amazing models that could produce synthetic video images that really look like that. We're a long way from doing that, obviously. Going on with the same experiment, of course, we didn't observe everything, but suppose we assimilated that movie loop and we went to the other side of the Earth, somewhere of the ocean, and we had, I don't know, a Cygnus instrument or a SSMIS instrument. These are instruments that only measure wind speed or the square of the wind, say. And on these replicate Earths, you know, there are different U values. So on the x-axis here, I've got U. You see that cursor. On the y-axis, I've got U squared. So there's the parabola. On each Earth, an observation of U squared will be made. The model variable is U, but the observation is going to be of U squared. And there'll be some error of representation that'll be different on each Earth, and there'll be some instrument error that will be different on each Earth. So these black dots, these black crosses represent the observed values on each of these Earths. And they're different to the true value because of those observation errors. You can notice that there's more spread, say here where the true value of U is 2 and U squared is 4. You can see there's quite a lot of spread in what the observations might be corresponding to that truth, whereas down here near 0, there's hardly any. So there's a good reason for that. And just think about it. So suppose you have a reasonable instrument of U squared, and you're near 0, yeah? So if the instrument designer has included information knowing that U squared cannot be a negative value, yeah, it's U squared, has to be positive, but at the same time, they've managed to make an unbiased instrument so that when the truth is near 0, the average of all the sort of random observation errors, given that truth you might have, are going to average to 0, then kind of this spread of observation errors has to get smaller. Do you see that? It's because the biggest the error can be on this side, you know, it could be down there. That's not a very big error. And so if on average, these ob errors are going to be 0, you can't be very big on this side as well. So you can see that. So if you've got unbiased observations of these bounded variables, you should anticipate that the observation error variance will get smaller as the truth gets closer to 0. Yeah? I mean, you have to think about the specific observation type. There might be some observations where it'd be quite happily to give you a negative value for U squared. And if it does that, you know, what I'm saying wouldn't apply. But you just, when you hit these bounded variables, don't expect that the observation error variance will be independent of the state. Alan Gear showed us diagrams just showing the innovation variance associated with cloud-affected radiances. And you can see it was a function of this average of the background and the ob. And you know, we should expect that. So you need to look at that. And we need techniques developed to deal with that. Okay, so that's one point I want to make. So in dealing with these bounded variables, anticipate that the ob error variance will be a function of the state and try and account for that somehow. Now, let's suppose on our Earth, we get an observation of y equal 1.71. I can collect together all the Earths where you also got an observation of y equal 1.71. And then I can plot those as distributions, which is what I've done here. You can see, so these crosses along this line, they're all Earths where we had an observation of 1.16. And then I can, if I make the ensemble size bigger, I can plot densities. And so the posterior density of U is bimodal because the observation was of U squared. In observation space, you can see the prior is this black line, so you've got to like put your head on the side to look at this. But the x-axis is the density of U squared of the prior ensemble for the solid line. That's the prior. And you can see that the most probable value is 0, actually, and then it tails off. So, you know, that is completely non-Gaussian. When you have a bounded variable, Gaussian will be a horrible assumption, particularly if the bound is a possible value. So things like rain and cloud, you know, it's actually often more likely that it'll be 0 than it'll be anything else. Anyway, the posterior, because of this sort of structure that's associated with the ob error that I assumed here, the posterior is this dash curve. And that also, well, it's more Gaussian, but it's not exactly Gaussian. It's actually a gamma PDF. So clearly non-Gaussian observation space. And then a model space, well, I guess a Gaussian mixture might work, but you know, it's not a single Gaussian. So, I just said that. If we were to do this very simple 1D problem, say using 4D var with no outer loop, which quite a few centers are doing, or you were to do an Ensemble Kalman filter, and you were trying to compute the posterior density from that, then in UU squared space, what you'll get is these circular dots here. So it looks bad in observation space. It also looks bad. I mean, there's some things that, like the posterior mean of U probably isn't that bad, but the whole distribution is very bad. Yeah? So this red line is what you get from an EnKF or a variational technique that didn't have an outer loop. So it's failing due to linear Gaussian assumptions. If you were using a version of 4D var where you insisted that I'm going to treat the observation error variance as if it was, the likelihood, the observation likelihood as if it was Gaussian and independent of the state, and that my prior was Gaussian, then the nice thing about 4D var with an outer loop is it ensures consistency between the U and U squared values. So these, you can see these blue dots that you get with 4D var with an outer loop would be exactly on the parabola that they should be on. But the density's all wrong. The density's wrong in the posterior densities are wrong in observation space. That's that blue line. You can get the mode. And in model space, it's wrong as well. Arguably, at least it's got a hint of bimodality. Maybe it's a bit better. But that's failing due to the Gaussian assumptions of the 4D var formulation that I used there. So the challenges, observations of bounded non-Gaussian variables. If they're bounded and the mean and the standard deviation are of a similar size, the distance from the bound is similar to the size of the standard deviation, it will be very non-Gaussian. I didn't talk about this yet, but there's also on-off variables like rain, high probability of getting 0. EnKFs 4D var and particle filters as well are very unsatisfactory for that. But that's what we have in the atmosphere. We've got these variables where 0 is really likely. Yeah, clouds and precip are all like that. So we've got to be able to handle that situation. There's nonlinear relationships between model variables and observed variables. So var with an outer loop accounts for that. Leonhard Scheck gave an example of this for the EAKF, where he's getting these weird results between sort of ob space analyses and model space analyses. So I'm going to talk about a method that addresses uncertainty distributions associated with bounds, and this will just be associated with a bound on one side, and also nonlinearity. So it deals with both of those things. And then I'll finish up by talking about a way this method could be incorporated in other methods. Okay, so the method I'm going to describe fits beautifully into, well, in principle, I still don't have it there, unfortunately. In principle, it would fit beautifully into the data assimilation research testbed algorithm, the Ensemble Kalman Filter that Jeff Anderson developed. And these are basically the 3 steps in it. You go through the observations one by one. You do univariate Gaussian assimilation, so this is the Ensemble Kalman Filter, of the first observation, and you obtain a posterior ensemble of analyzed values of that observed variable, and then you regress away from that ensemble of the difference of the ensemble of analyses from the corresponding ensemble of forecasts. You regress away from that to all the other observations. So y in my notation is an observed variable, and x is a model variable. You also regress away from those differences to the model variables. And then, okay, we've assimilated the first observation. So these guys here, they're a posterior. So, but they become the prior, that's what I'm doing there, for the next observation. So that's how you go around the loop. So that's just a simple summary. And all I'm going to do is adjust this so that it's suitable for bounded variables, and also that it accounts for nonlinear relationships between the model variables and the observed variables. Okay, so I've sort of mentioned this. When you've got a bound, a Gaussian's not going to be good because it'll happily give you negative values. In contrast, a gamma PDF is positive definite, so it doesn't do that. It's also nice because it gives finite densities for 0. inverse gamma PDFs are a bit like log normal PDFs that you probably all know. Notice that when the mean, this distance from the bound, when that is big compared with the standard deviation, it actually kind of looks Gaussian. So there's sort of a limit where these things basically look Gaussian, and the Gaussian assumption would be good. The problem is when the mean and the standard deviation are almost equal to each other, for, say with a gamma, that's what you get. It becomes highly non-Gaussian. So one way of dealing with this is you might dream up actually for log normals and gammas, I know of functions that will make these Gaussian. So you could do a Gaussian anamorphosis approach, in which you would take a nonlinear function of the variables, and then they'd be Gaussian. This is problematic for a couple of reasons. One is, if you take a nonlinear transform of the observation, and the observation itself has unbiased error, yeah? If that transformation or function is nonlinear, then now you will have an observation of that nonlinear function that is biased. Yeah, it's because it's like if the error delta x is, the mean of that is 0, the mean of delta x squared is not going to be 0. Yeah, these things get folded in, and it depends on the nonlinear function. So you're giving yourself a biased observation whose bias will depend on the prior uncertainty. So it's not going to be an easy bias to estimate, given that you've got flow-dependent uncertainty. In model space, you might do something where you say, okay, well, I'll deal with the observed variable. That might be a nonlinear function of the state, but I'm going to change my model variables to be Gaussian through transformation. If you do that, and say you did an Ensemble Kalman filter, then you may, often you'll see situations where while you stay in the transform space, say with an Ensemble Kalman filter, you'll have the nice property that the variance of the posterior ensemble will be equal to the mean square error of the mean in transform space. But when you undo that nonlinear transformation, typically that will not be true. And this is a little example from a paper of mine that just came out where I did the log normal approach. And it was interesting. In log space, like if I keep everything in log space, it's fine. The mean square error in log space is about equal to the ensemble variance in log space. But if I undo that, if I undo the log and look at the raw variable itself, then actually in this case, the ensemble was over-dispersive by a factor of 2. But there are other techniques that pretty much get it right. So yeah, Lars Nerger gave us an example of issues associated with log transforms as well for biogeochemical situations. So I don't know, there seem to be problems associated with the anamorphosis approach. Okay, so let's just think about, okay, here's a bounded variable. Let's suppose it's got a gamma PDF. That's an example of a gamma PDF. Could be a concentration, say a biogeochemical concentration. Then we get an observation, and we need to characterize the error of the observation. And we might go to the instrument designer, and he'll tell us, well, look, if the truth was equal to 1.5, then this is the distribution of observations you'd get. And in that case, that function you're seeing there is not a gamma PDF. It's actually an inverse gamma PDF. So that's the distribution of possible obs, the distribution of possible obs given a truth. But of course, what Bayes' theorem wants is you fix the ob and let the truth vary. You let that C vary. And if I do that for that observed value, so the actual likelihood function that you'd use in Bayes' theorem, given that the observed value was 1.5 here, is actually this function here. And so that dot dash function, that's what the likelihood function is. And Bayes' theorem tells us to get the posterior, we multiply the prior with the likelihood, and it gives us that curve there. So in this paper, in QJRMS, came up with a way of, well, just showing that the posterior mean for that situation with gamma prior and inverse gamma observation uncertainties, the posterior mean is actually given by this equation. This term here looks a bit like a Kalman gain, but actually the P is a relative forecast error variance. So it's the variance of the prior divided by the mean squared plus the variance of the prior. And the same is true for the observation error variance. In that paper, there was this extreme limit when there was a lot of uncertainty in the prior and a lot of uncertainty in the likelihood, where I wasn't quite producing Bayes' theorem. I basically set it up as a perturbed obs type approach. Anyway, I figured out how to fix that, so now it's good for all the moments. Okay, so we're going to test. I'm just going to show you a little test of that algorithm against an Ensemble Kalman filter. As I was saying, there's quite a few instruments that measure something like wind speed. So Cygnus is one, SSMIS is one, so surface wind speed. People are excited, well, were excited about Cygnus for the possibility of getting wind speed observations underneath tropical cyclones. So the arrows here show the wind speed associated with something that looks like a bit like a tropical cyclone mesh, you know, lying within some large-scale wind fields. So that's, I set this up so it's got random numbers to produce these sorts of states. That's one example. That's another example. I can produce gazillions of these samples. I'm going to do a perfect model test, if you like, where I generate a 10,000 member ensemble like this. I let one of them be the truth. And then what I'm going to observe, instead of just observing U and V, I'm going to observe, say, kinetic energy, U squared plus V squared divided by 2. A lot of instruments measure something like that. And I won't observe everywhere. I'll observe at every 6th grid point. And the distribution of random observations given the true kinetic energy is going to be an inverse gamma PDF with a relative variance of 0.25. So I'm going to do that experiment, run many independent case. So here I've got 8 sets of 8 sets of 50 trials, all independent. And you can see in each of those trials, the mean square error in the analysis of kinetic energy is always better when you use GIGG, this gamma inverse gamma variation on the ensemble adjustment, rather than if you just use the normal Gaussian assumptions of the ensemble adjustment Kalman filter. But of course, the GIGG is just a rather minor variation on the ensemble adjustment Kalman filter, I should say. That's true at OB sites. It's true for the correlation. So that's a lot better. So that sort of worked out. That's what we get by making a better assumption. Notice that, you know, U squared plus V squared, that's not exactly gamma, yeah? It's not perfectly matching that gamma assumption. It's just better than Gaussian, yeah?